Hey everyone, welcome to the lecture on the root and ratio test. So this is going to be the last part of the whole convergence testing for series. So 2 more tests to go. The first one is the ratio test. So again, you have a series where the sequence inside is a sub n. They have to be non-zero, but they could be positive or negative. And the ratio test just gives us a way to classify convergence or divergence based on the ratio of sequential terms. So you just stack the n plus 1th term over the nth term, let n go to infinity, compute that limit, and then the ratio test tells you about convergence or divergence based on what that limit is. So if p is 0, anything from 0 to less than 1, then we get absolute convergence. Anything bigger than 1, and if it's infinite, we get divergence. And if it equals 1, we don't know. We don't have any information. So let's do some examples with using the ratio test. So this is a sub n. Then I compute rho as the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which is the limit as n goes to infinity. The n plus 1th term is 2 to the n plus 1 over n plus 1 factorial over, and I take the absolute value, just the nth term, so 2 to the n over n factorial. Every term inside this expression is positive, so I actually don't need the absolute value symbols. And I'm going to go ahead, remove those, and simplify in one step. So on top, I'm going to have n factorial times 2 to the n plus 1. And on the bottom, I'm going to have n plus 1 factorial times 2 to the n. And so I'll get some cancellation here. So n factorial over n plus 1 factorial is just 1 over n plus 1. Didn't do a very good job writing that. Okay, n plus 1. So you can see that everything cancels out except for that n plus 1 on the bottom. And then for 2 to the n plus 1 over 2 to the n, that's just 2. So I get this is the limit as n goes to infinity of 2 over n plus 1, which equals 0. Therefore, again, looking at these results, we're in this situation. If p is bigger than or equal to 0, but less than 1, then we get absolute convergence. It's always a little odd to me to say that a series converges absolutely when all of the terms are positive. So of course, absolute convergence implies regular convergence, right? Like since they're all positive, they're kind of one and the same. We'll see later why they talk about this, because we're going to introduce a variable x into this and talk about the radius of convergence. For B, all right, so our a sub n here is just n to the n over n factorial. And we also know that our a's are bigger than 0. So I just want to compute rho. It's the limit as n goes to infinity of a sub n plus 1 over a sub n. So I get n plus 1 to the n plus 1 over n plus 1 factorial over n to the n over n factorial. And again, everything in here is positive. So I can remove the absolute value notation. And I just get n factorial times n plus 1 to the n plus 1 over n plus 1 factorial times n to the n. So this one, I think, is very fun. All right. I'm going to separate a few terms. You might think, oh, I can cancel out the factorials, which you can, I guess. Okay, fine, we'll do that first. So the first thing I'm gonna do is I'm gonna cancel out my factorial. So I get 1 over n plus 1. That's exactly what we did last time, up here in pink. So, and then I'm not gonna do anything with this just yet. So I get n plus 1 over n to the n. But now I'm noticing that I can cancel out one of these n plus 1. So I get the limit as n goes to infinity of n plus 1 to the n over n to the n, because one of those copies of n plus 1 cancels. And then I can go further and say that they're both raised to the same power. So this is n plus 1 over n to the nth power. And then I'm going to rewrite this as something that may be more familiar to everyone. So this is 1 plus 1 over n to the nth power. So this is a really common thing that on the test people did not do successfully. They would see a limit like this and they're just like, oh, well, that's just like 1 to the infinity, and 1 to the infinity is, 1 to anything is 1, and blah, blah, blah. We saw that with the infinity to the 0. So those are still indeterminate forms, and it's not really abundantly clear that we can just adhere to the same algebraic rules with exponents. So first of all, this is a very popular limit. It's Euler's number. So hopefully that's something that you recognize. But in general, if you want to compute that limit, just because we're on a different section doing a new topic doesn't mean that you don't have to still use L'Hopital's rule. And when you use it, you have to show it. And you have to continue to justify your work, even though maybe it's something that we did 3 or 4 sections ago. So to evaluate this limit, you're going to let L equal the limit as n goes to infinity of 1 plus 1 over n to the n. Then you can take the log of both sides, and the log of the limit is the limit of the log, provided everything's continuous and stuff exists. So now you're going to have right, so now we have this 0, we have infinity times 0. So what we want to do is further rearrange it so that we have zero to 0. So now I can apply L'Hopital's rule, right? Because this is 0 over 0. And so if I take the derivative of this, no, this is a mess already, that's okay. On the bottom, I'm just going to get negative 1 over n squared. And on the top, I'm going to have 1 plus 1 over n. And then I'm going to have negative 1 over n squared. So now this will simplify into 1 over 1 plus 1 over n. So as n goes to infinity, this goes to 1. So now we have that ln of L equals 1, which is the same thing as saying L equals e to the first power, L equals e. So the limit of this is e. Rho is equal to e. E is bigger than 1. So this guy diverges. And then I think we have one more example. Okay, let me scooch this stuff down real quick. So our last example is C. So what you want to do is continue to compute rho. And we're going to take the absolute value of a sub n. And so now we have, this is an alternating series. So now it kind of makes more sense to talk about absolute convergence here also. So when we determine rho, it'll tell us absolute convergence, but then we know implies conditional convergence. So this is -1 to the n plus 1. And then everywhere you see an n, make sure to add 1 to it, and make sure to do that very carefully. Really quickly, I just anticipate people making this mistake. It's not going to be 2n plus 1 factorial. It's going to be 2 times n plus 1 factorial, which is 2 times 2n plus 2. So that's something to be careful of here. All right, so now if I take the absolute value and then simplify, I'm just going to rearrange it so it's on a fraction of fractions. So the negative ones go away. I get 2n quantity factorial on top with my n plus 1 factorial quantity squared. That's hideous. Okay. And then on the bottom, I'm going to have two n plus 2, just expanding that out, factorial, and n factorial squared. So something to realize here. So 2n factorial equals 2n times 2n minus 1 times 2n minus 2, etc. And 2n plus 2 factorial equals 2n plus 2, 2n plus 1, 2n, 2n minus 1, etc., and so on. So when I cancel these out, everything's going to cancel except for these two guys here. So I just get 1 over 2n plus 2 and 2n plus 1. So that's the first piece. So 1 over 2n plus 2, 2n plus 1. And then for the next piece, what I'm going to do is I'm going to move it, let me do it like this. I'm going to move it so they're just one whole thing being squared. So then it's n plus 1 factorial over n factorial, and that whole thing is being squared, right? So I can, because they both are raised to the same power, I can do this. And then n plus 1 factorial over n factorial is just n plus 1 squared. So this is the limit as n goes to infinity of n plus 1 squared over 2n plus 2, 2n plus 1. And so just as a polynomial of equal degrees, this is going to be 1/4, which is less than 1. So we know that our series converges absolutely. The next and last test that we have is the root test. So this is really useful when you have things raised to the nth power. The ratio test is more useful when you have things that are factorials, because factorials cancel really nicely when you're looking at subsequent terms. But we still have the same result structure here. So if p is greater than or equal to 0 but less than 1, we get absolute convergence. If p is bigger than 1 or infinite, we get divergence. And if p equals 1, it's still inconclusive. So looking at example 5.24, rho would be computed as the limit as n goes to infinity of the nth root of the absolute value of n, a sub n. So this is n squared plus 3n to the nth power over 4n squared plus 5 to the nth power, absolute value. But these terms are all positive inside, so I don't really need the absolute value. So I get the limit as n goes to infinity, the nth root of n squared plus 3n. And I can actually combine, because they're both being raised to the nth power, I can combine this like this. Oops, excuse me, that should be n. And so this is convenient because when I take the nth root, I'm just going to get cancellation of that power. So I just get n squared plus 3n over 4n squared plus 5. So again, this equals 1/4 coincidentally. So we know that in example A, we get absolute convergence. In example B, we compute rho in the same setup. I'm going to go, this is a typo I think I found in the book. I don't think the series should start at 1 because it's undefined at 1. So I'm going to say that it's 2. So I'm going to get the absolute value of n to the n. Now, the natural log of 2 is a negative number. But once it hits 3, it'll be positive thereafter. And when it comes to the convergence or divergence of series, think about the fact that you're adding up an infinite amount of values. So one value being different, like if I were to switch the sign on one of the values, it wouldn't change whether or not that series converges or diverges. So if I wanted to, like, if this thing converges, right, starting at 3, then n equals 2 would also converge, right? Provided that a sub n is like some finite and defined number. So in that respect, I can kind of ignore the absolute value symbols. Oh, and you know what else I just realized? When n is 2, it'll be positive because it's getting squared anyway. All right, there's my cheat. Cool. I don't have the guilt of details. So I'm going to remove the absolute value symbols. I'm going to group my exponents together as I did above. And then I can go ahead and simplify this. So this is the limit as n goes to infinity of n over the natural log of n. And so because this goes to infinity over infinity, we can apply L'Hopital's rule. So when you use L'Hopital's rule, make sure to at least write an LH over the equality symbol. So this is the limit as n goes to infinity of 1 over n, which is the limit as n goes to infinity of n, which is infinity. So we know that our series diverges. There's one more thing I wanted to talk about. I don't feel like it's that common to like see a sequence in the wild that I want to compute the sum of, but what is a really natural thing to do, and we'll see this later on, is to construct a Taylor series or a Maclaurin series around a value x, and we might want to say something like, well, for what values of x would this series converge? So you construct Taylor and Maclaurin series to approximate the curved natural things. Like they're super, super useful. They're probably the most useful thing in the class. So if I construct a Taylor series, I want to know for which values it'll converge. And so now we're going from, hey, does this thing converge or diverge, to, hey, what would make this thing converge or diverge? So I want to throw in a variable. So let's consider this. We'll call this star heart happy face. Okay, so exciting. So consider the series n equals 1 to infinity of x to the 2n over n squared. Right, so let's say we construct a Taylor polynomial and it looks like this. So now I want to know what values of x will this converge? So let's try doing, I'm going to go with ratio test. So if we use the ratio test, now remember that X is just like a variable, totally rogue. The indices do not affect X. Like as n goes up, X is just this unknown quantity X. But it is getting raised to the nth power. So the ratio test will give us rho equals the limit as n goes to infinity of x to the 2 times n plus 1 over n plus 1 squared over, and remember we're taking the absolute value of this, x to the 2n over n squared. So now this becomes x to the 2n plus 2 times n squared over, and because I don't know what x is, I still have to keep these absolute values on, over x to the 2n times n plus 1 squared. So I'm going to go ahead and simplify a bit further. So this becomes, these guys here, n over n plus 1, that's always positive. So this really just becomes the absolute value of x squared times n over n plus 1 squared. And notice that the limit as n goes to infinity, n is going to infinity, n, not x. So x is really just like not even factoring into what this limit is. So I get that the absolute value of x squared times the limit as n goes to infinity of n over n plus 1 squared, which is just, this limit is just 1. So I get the absolute value of x squared equals rho. And if my series is going to converge, then we need rho to be less than 1. So you just set up what you got for your limit to be less than 1. So the absolute value of x squared is less than or equal to 1. So this is really just a lot of times for radius of convergence, people will say absolute value of x is less than number. That's kind of like the setup. So if you want to compute a radius of convergence, that's how you do it. You let x be arbitrary, and then you go through either the root or the ratio test or whatever test that you feel would be appropriate to determine, like, hey, this converges for all these such values, and then figure out how x plays into that.